for radiation hardening, other about physics, where we go deeper in details on what is radiation, in fact, and also about applications with robots. Then after, we have a poster session, which is a clash between French student and Japanese student. So you will see on each spot for the poster, one poster from Japan, one poster from France. And the idea is to exchange, speak English, Japanese, or French. You choose your language. Then after, we have a visit of the IMS lab during 30 minutes on our platform for circuit design and measurements. And then after, very important, we have a social time, which is a French lunch. And I think our colleagues from Japan now are used for our French diet since several days. Okay, so thank you again to be here. And now I give the floor to Maxime.
Thank you, François, for introducing me. Maybe I should start my PowerPoint. Okay. So my presentation is about a voltage reference in CMOS technology desensitized to the dose rate in harsh radiation environment for the dismantling of nuclear power plants. Before to start my presentation, we'll see why do we need a voltage reference. Actually, our final goal is to build a radiation-hardened circuit to contribute to the dismantling of the aging nuclear power plants. We start with a voltage reference, then we make it hardened to the radiations, and then we export this methodology to other circuits. We start first with the voltage reference because it's a circuit that allow other circuits to work. So it's a great idea to start by one. My presentation will be divided in 3 parts. First, I will explain the impact of radiations on electronic devices. Then I will go ahead and show you the radiation techniques, the radiation hardening techniques on electronic devices. And finally, I will explain my voltage reference and how I make it robust against radiations. So first, let's start with the impact of radiation on electronic devices, starting with the dose rate effect and then the dose effect. Here is a PN junction, which is really common in nanoelectronics. A PN junction is a diode, and when a diode is submitted to a radiation beam, like a dose rate radiation beam, it transforms into, it behaves itself as a current generator, which is super cool when you try to make photovoltaic cells, but not when you are trying to build a circuit. This current generator can be expressed with the following equation. The current generated is equal, in amperes, is equal to the dose rate of the radiation received by the PN junction, the electron charge, the constant carrier, the PN junction area, and the dimension of the PN junction area. By taking a measurement on my layout, we can determine the current we will have depending on the dose rate, which is this curve over there. To put you more into context, here is an example, multiple example of the radiation dose rate that you can meet in everyday situation. Our expectation is to be in nuclear power plant underneath this range of dose rate. The dose rate should not have a lot of effect onto our circuit because it is too small. Actually, I said our expectation, but it's more like where we will have to start, where we will start to have problem with the dose rate. Now that I have shortly explained what the dose rate will do on our circuit, let's talk about the dose effect. Here is a NMOS transistor, and when we put a dose of radiation on it, is the threshold voltage way lower and lower. This is due to is caused by the oxide being broken and the charge accumulation in the silicon. So this is the only thing you have to remember for the next part of the presentation. Now I will explain the hardening techniques of electronic devices. First, I will explain which technology you have to use to make your circuit harden. Then I will explain the hardening by layout, and finally the hardening by design. So let's start with the hardening with the technology. By default, you will probably choose a bulk technology. Here's PMOS and MOS. You will probably choose a bulk technology because it's low cost, it's widely used, and it has a wide range of application. The problem of bulk technology for radiation hardening is that it's barely tunable with bulk body biasing. It has a lot of PN junction, so there is one in reverse. A lot of PN junctions that will generate photocurrents when submitted to dose rate. And finally, it has important oxide. So when the dose accumulates into the oxide, the transistor performances will drift a lot. In our case, we choose to do the circuit with FDSOI technology, and here it's why. The FDSOI technology has multiple advantages against radiation. First is performance can be adjusted on purpose thanks to the backgate. So if we have problem because of radiation, we can tune the performances of the transistor and counteract the effect of radiation. FDSOI technology has a fully depleted silicon channel. So this means there is no PN junction inside the channel of the transistor. So there is no photocurrent generated through radiations. Another advantage is that transistors are built onto an insulator. So the PN junction, those PN junction will not impact directly the channel. On the other side, the FDSOI technology is really pricey. Is that not a wide range of use? For example, not a lot of digital. And finally, new technology means new fear. And for some people, if it's not the good old-fashioned way of designing, it's not a good way of designing. But we choose FDSOI. So now I will explain the hardening by layout. So here is again the cut view of two transistors, PMOS and NMOS, gate and source. And here are the backgate. As I said earlier, the backgate are used to tune the transistor performances, but they have the disadvantages that there is two PN junction in the backgate that will generate currents when there is a radiation. We can model those currents. You can simulate those currents with a real current generator and resistor to simulate the resistivity of silicon. A current flowing through a resistor make a voltage, which impacts the voltage of the backgate, which impacts the performance of the transistor. Our goal is to reduce those resistivity, resistor, and to reduce the currents. So we retain a three-way of doing it. Here is 3 times my voltage reference that I will explain later. For now, the schematic is completely the same, but the layout is not the same. On the first version, we have all the transistors are surrounded by a guard ring, N guard ring and a P guard ring that will drain current generated by the PN junction in order to reach an as small as possible resistivity of to drain currents from the PN junction. Another configuration is aim to reduce as much as possible PN junction size, so to reduce currents. And finally, the last configuration is to make the PN junction far and far from the transistor, so the impact will probably be reduced. Now I will explain the hardening by the design, which is more for the dose. The dose effect, if you remember this slide, as the dose increase, the threshold voltage of transistor decrease. This effect can be reduced by using not only 1 but 2 transistors, and by subtracting the 2 lowering threshold voltage against the dose, we can get a constant threshold voltage against the dose. We can do this by simply stacking the 2 transistors one on each other. Now that I explained all the radiation techniques I have in my bag, I will show you what I did on my voltage reference. My voltage reference is based on this circuit. The 2 stacked transistors have decreasing threshold voltage with the temperature. So with the 2 decreasing threshold voltage against the temperature, we can create 0 temperature coefficient voltage reference. And actually, this is exactly the same we are doing for the dose, as this is just the example I explained before. This is the full topology of my voltage reference. So you just have the 2 stacked transistors that I just explained, and here is simply a current generator to polarize the circuit. With this, we can reach 210 ppm per degree at about 50 millivolt of voltage reference. It's not perfect even in this state of the art, but already something great for radiation hardened circuit. So what is next onto this voltage reference? I have already done the layout, and it's for now still in manufacturing. Actually, we received it last week. So we have done a multiple layout of this circuit to benchmark every configuration I explained before of the PN junction and guarding against radiations. So now we are waiting for the circuit to come back from the foundry so we can expose it to radiation and test it. Then after this, we will have to validate all aspects of our radiation test bench and of our layout design techniques so we can design more radiation hardened circuits. And finally, we want to explore other radiation hardening techniques like the threshold voltage compensation through the backgate, especially for the dose effect. So we could decrease the backgate voltage to re-augment the threshold voltage to counteract the dose effect. For the end of this presentation, I will conclude on what do you need to build a desensitized to the dose rate circuit. First, you have to choose a good technology. For example, the 28 nanometer FD-SOI just as us, for the reason I explained before. Then you have to design a circuit that is based on threshold voltage subtraction, so you don't have the dose effect, or that is low threshold voltage dependent, again, to reduce the dose effect. And finally, you have to wait for my result of measurement to know which configuration of wiring and PN junction is the best for the layout. So thank you very much for listening my presentation. It's over. And if you have any questions, feel free to ask.
Thank you very much, Maxime. So, any question? Yes.
Yes.
Thank you for this excellent presentation. I have a first question. It's what is your a priori? What do you think is the best solution with the 3 layout a priori? Well, of course, you need to wait for measurement, but still, what is your feeling about that?
For me, the third one, as this is the resistivity is really lowered by all the wirings, and the PN junction is really far from the transistor. I think we can drain the current before it goes through the backgate. So we'll see.
Thank you.
On the other side, this technique takes a lot of place. It's not on scale like the deep and well is much more far away from the light yellow one. So it takes a lot of place.
So it means that if it works, any of those 3, all the design that has been done previously for, let's say, regular or general purpose will be usable for radiation just by changing the layout of the circuits, adding these, let's say, wirings under the transistor.
Yes, but we'll have to increase the space of the area taken by the circuit, but yes.
Nothing came for free. You know,
Yes.
that's already a good thing if you don't have to redesign the microprocessor from schematic point of view. You just have to, let's say, spread across a little bit.
Just the layout, yes.
Thank you so much.
Any other question?
Thank you very much for the presentation. My question is also in this slide.
The last one?
This one. In the middle configuration, you use that gathering. It's like a line.
Yes.
So where do you place the line? I think that we have 4 choices. Top, bottom, right, left.
Yes.
How do you place that?
This one is the pretty regular one, like the one you put by default on the circuit. I mean, it's not really a normal circuit is already like this, except for the pig wiring around the transistor. But the backgate with only 1 trench is already what we do regularly.
Can you rotate?
Rotate, oh yes. I put it on the bottom, but you can put it on top. Like, for example, we could merge this red line with this red line over there, and it takes a little bit less place. Is that what you ask?
Is this placement is best one for the radiation, or you can rotate maybe better?
To rotate the red wiring to be better for radiation? Is that?
Now, right.
Oh, yes, yes.
If you rotate the configuration, how much?
Actually, it's just it's not the real layout. It's just for too much with the transistor on the schematic. But yes, if you tweak the layout, it can be more space economy and better in radiation. Yes.
Yes.
Thank you for your presentation. Could you provide us with some more information on how, where, and when will you be able to expose your circuits to radiation?
O is with LP2I, Laboratoire des Eaux Infinies de Bordeaux. When probably January. And I don't have the PCB yet, but in 3 months it will be ready to go into radiation. And O, I have some package without the lid, so the radiation can go in it freely without any disturbance.
I have a question for you. The check with radiation, with stress voltage, the major issue for you, or they are also affected by radiation on the transistor?
This is the main issue with the dose, I will say. But and actually, it will be mostly the one that appears first before the dose rate. Because the dose rate, you have to go like yes, you have to go like 1 million rad per second to have real effect, like to create some microamperes in the circuit, which is a really big 1 million rad per second. Like as the chart show, the military standard for USA and for space is only 300 rad per second. So we are far above. But the dose rate, the dose.
Any other question? Very good. Thank you again, Maxime. Thank you.
Yeah.